Okay, hello everyone and welcome. Let's go ahead and get started. Very guys. Glad to see you here today. I wanted to start off by just taking a quick peek at the calendar because we're getting pretty close to the end here. Want to make sure everybody knows what's coming up, what things are remaining in this class. Actually, today is kind of a big day, kind of an important day. Today we're covering Module 9, which is the last official module in the entire course. So after today, um, we're not going to introduce any new material that will be on the upcoming exam, for example. This is the last new module of new material that you can expect to see on the exam. You'll notice, however, that the exam is not next week, but it's actually the week after. So we actually have this whole week in between this week when we're covering Module 9 and then our Exam 3 review, and the exam is not until the week after next. I want to assure you that we are having class next week. We will have class here on Monday. We also have a studio planned for you next Wednesday. This is kind of bonus material, so it's going to be covering some content. Uh, Basically, we're going to be talking about the idea of how do I write code that doesn't just work, but works well. So caring not just about getting things to be functional, but also getting things to be written well, right? Clearly, we can convey ideas in many different ways. You've seen that probably over the course of the semester when writing your own code. So we just kind of want to talk about code quality and some things to look out for. It's something that both Professor Nuri and I care about and have spent some time working on in our other classes. So that's going to be the topic that we're going to be talking about in class next Monday, and it's also going to be the topic of the final studio, which is going to be taking place next Wednesday. And then the week after that, that's where we're going to be doing our Exam 3 review and our third exam. And then notice that the final exam is scheduled for May 1st during the normal final exam week. So just want to make sure everybody is aware of what we've got coming up. We've got two more studios. We've got two more quizzes, including one that we're going to do today. And then we've got two more exams, although you do get to drop an exam. So keep that in mind as well as we come up on the last couple of exams here for this class. Does anybody have any questions about the course calendar, about the logistics, about what's coming up over the next few weeks before I hop into Module 9 material for today? Everybody feel comfy about what's going on, about what to expect next few weeks? Awesome. All right, great. So then today's topic, today's material is kind of a sneak preview in a sense of what we hope you will see if you choose to go on, take future computer science classes. So one of the more common slash heavily recommended classes for students to take after taking this one is the data structures class. That is class CSE 2407. And it is a hugely important class in the world of computer science. It is a prerequisite for basically every upper level computer science class that we offer here in this department. Turns out the way that you structure your data has a huge impact on the code that you write and how your programs work. And so that class is going to show you a bunch of different data structures, a bunch of different ways to structure your data, and talk about how those data structures work in a very detailed level. We're not going to be talking about data structures in that level of detail today. Our purpose for today is just to introduce you to a couple of new data structures, play around with them. These are going to be some of the more common data structures that you might expect to see if you're going to be writing code. We're not going to go into the nuts and bolts of how these data structures work a whole lot, but we are just going to show you how to use them, how to take them for a spin. So that's kind of our goal today, starting with lists. So lists are a very great data structure to start with because they feel very much like arrays in a lot of ways. And so a lot of what I'm going to do with this first example is kind of compare and contrast the use of arrays, which is a data structure that we are already familiar with, to lists, which is the new data structure that we're trying to introduce you to today. So for example, if I wanted to create an array that represented a rainbow, right, and just has all the colors of the rainbow in it, we could start out by creating an empty string array. This is all review, right? That's why I'm going kind of quickly. There are 7 colors traditionally in the rainbow, right? And then I can go through and I can start placing those colors into my array by saying things like this. Take the string red, store it at position 0 within the array, and then we would continue on and probably What's the next color? Orange would be the next color. Oops, orange. Spelling is not my strong suit. That's okay. And then yellow. You get the idea. I don't think I need to do all 7 colors, right? You get the idea of where I'm going with this. And then later on, let's say I wanted to, see the contents of my array. We talked to you way, 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 way back in module 3, week 3 of the class, that we can write a for loop, right? That starts at 0, goes to the length of the array, and then simply prints out the contents of our rainbow array one item at a time. In this script, there's no reason not to use arrays to do things like this. I think this is a great example of when I might wish to choose an array in my program if I'm doing something with rainbows in this fashion. This seems like a perfectly reasonable approach to me, but there are some issues with arrays. There are some inconvenient things about arrays that you've probably run into as you have worked on assignments and such over the course of the semester that lists do a little bit differently. The biggest and perhaps most famous constraint with arrays is this right here. When we create an array, we have to say how big the array is, and then the array is forever that big. In some situations, that's not a problem. But in other situations, it's pretty inconvenient, right? In some situations, I wish that my array could grow or shrink depending on whatever it is I'm trying to do. But that's not possible. If we run into that situation, we have to create a new array that is bigger or smaller depending on whatever the case may be that we're trying to accomplish. So lists try to solve that problem amongst many other problems. Another big difference between arrays and lists is that lists in Java are objects. Lists in Java, they use classes and objects. So all of the rules that we've been talking about the past couple of weeks apply. I have to call a constructor to create an instance of a list. And then once I have that instance of a list, I have to call methods upon that instance, just like we do for all of our objects. In fact, we can take a look at the list API, which I think is a great thing to have, at your disposal when you're working on coding using lists. And we can see that, okay, lists have methods called add, and lists have methods called get, and lists have methods called size. So instead of using what we know from our arrays, we have to shift our thinking a little bit and try and use these methods, create an instance of a list and use these methods instead. What I would like to do next with you is take this code and rewrite it using lists. Take this simple array example that we're already familiar with and try to rewrite it using lists. So instead of using a string array here, I would like to use a list of strings. This is how I would say the equivalent thing using lists. Notice that the square brackets are gone. We're now using angle brackets is the term for those pointy brackets, right? So if you see those square brackets, I still want your brain to think arrays, but if you see that angle brackets, now we're talking about using one of these more advanced data structures, one of these object-oriented data structures, right? So we can leave the variable name the same. We can still call our list rainbow if that's what we want. But over here, we have to call a constructor. We're creating an object. So we have to call a constructor. And the way that we call a constructor, we actually have the first part. That new keyword is going to stick around, but then we have to say what it is that we are constructing. In this case, I'm going to construct what's called a linked list. You may be noticing, actually, wait a second, the thing that I typed over here on the right-hand side does not match the thing that I typed over here on the left-hand side. And that's actually, a very important observation to take into account. On the left-hand side, we're using list in a general way. On the right-hand side, we are using a specific kind of list. So there's not just one kind of list that exists in the world. There are many different kinds of lists that exist in the world. The way that we interact with those lists is the same, regardless of what kind of list it is. I add things to it, I can iterate through it as I'm about to show you, right? I liken it to thinking about different engines in a car, right? If I'm performing certain tasks, I might want a bigger engine. And if I'm performing lighter tasks, then I might want a smaller engine. Just same thing for lists. If I'm performing a heavy duty programming task, then that might tell me that I want a particular kind of list that can do that kind of heavy duty lifting. If I'm not doing a heavy duty programming task, then maybe I can use a lighter list that isn't going to take as much gas to run, right? It's kind of a similar idea with programming as you would see with machinery or any other kind of thing like that. So the types of lists that you might see here on the right hand side, linked list is a common one. Array list is also another common one. I honestly don't care which one you use for the purposes of this class. Does not matter to me at all which one you want to use for the purposes of this class. What is important to me is that you understand that, okay, this is calling the constructor. This is going to create an empty list, an empty list. And you can see that I've got errors right now. Those errors have to do with the fact that I need to import these things. And the easiest way that I've found to do that is to just hover your mouse over the thing that it's upset about and click this quick fix link, and it recognizes that list is a commonly used Java utility, so we can import both the list and the array list as needed. Okay, so we have now successfully converted our rainbow variable. It was an array of strings, but now it is a list of strings. And the line that I have here is calling the constructor. This is now an instance of the array list class. So if I want to do this, the equivalent of putting something into the list, I now need to use the methods that are available to me. So the one that I think is going to be relevant to us in this case is probably the add method. You can see the documentation says it just appends the specified element to the end of this list, which is interesting because that implies that unlike arrays, our list is going to be changing in size as I add and remove things from it. And that is in fact true. When we create an empty list, like we've done here, this list is truly empty. Unlike arrays, where if I created an empty array of strings, well, it would have 7 spots, but there would just be an empty string in each of those 7 spots. That's not what a list is doing. This is truly empty. The size of this list after I create it is 0, and it grows as I add things on to this list. So the way that I would change this line to reflect the fact that I'm dealing with an object now is to type the name of the instance, followed by the name of the method that I'm calling upon that instance, and then plug in the value that I wish to add to that list. So you can kind of see those are the lines where that's how I was setting values in my array from before versus the new line that I wrote at the top. I'm adding these things into the list. I'm kind of taking advantage of the fact that because this is the first thing added to the list, I know that it's going to be in position 0. And this is the next thing that I add to the list, so it will be in position 1, etc., etc. Orange. And I'll just convert this last one real quick. Okay. And then we're down to our last part of this simple example, which is to, iterate through the list and print out all the values from it. It's the same kind of process. It's just, again, we have to remember that we're not using an array. So that square bracket syntax isn't going to work here. Instead, we have to call the appropriate methods upon our list. So instead of dot length, if we take a look at the list API, we can see that, there is nothing here called length. But I do see this one called size. And it tells me that that's going to return the number of elements in this list. So that kind of seems like the equivalence. And then for this square bracket syntax right here, we're trying to retrieve a value from a list. Or the way that we would say that using the Java API is this method right here, get. Returns the element at the specified position in the list, according to the documentation. Well, that's exactly what we want. So instead of using that square bracket syntax, I would say rainbow.getI. And we've done it. We started with an example that used an array, and we converted it over to now use a list instead. And I can show you that it, in fact, does what I promise. I never actually ran it with the array. Maybe I should have, but here I am running it with the list and showing you that, yes, in fact, it does successfully go through this loop, print out all of the values that I added to this list one at a time, much like it would have if we had used an array instead of a list. I'm not done with this example yet. I just want to pause here to see if anybody has any questions about what I've done so far. I have a couple other things I want to talk about before I move on to our next example, though. Since I'm not, oh, yes. Yeah, that's a great question. The question is, do I have to add things one by one like this, or can I add multiple things in one go? As far as I know, you do have to add them one at a time like this. Yeah, there's no way to get all of those things in there. In fact, you may recall with arrays, right? We even had that extra syntax, the curly bracket syntax, where I could just do things like this. And there is no such syntax. So if we're trying to weigh pros and cons, there's kind of one right there, right? Arrays do have that extra little convenience that lists don't have. There are things that lists do that are really attractive, though, and that's kind of the next thing that I want to chat with you about anyway is like, okay, lists and arrays can kind of do similar things. So why would I pick one over the other? The biggest factor I think to keep in mind is how much data you think you're going to have. If you know up front, I have 100 pieces of data. Okay, arrays are great for that because I can create an array that's got 100 things in it, and I know that that's going to work perfectly for the amount of data that I have. If you don't know up front, how much data you have. If it's going to be fluctuating over time, like, oh, I have this much data now, but probably gonna have to add more stuff to it later, or maybe remove stuff later, right? Then a list is probably going to be a better tool for the job because it provides that flexibility where it can grow and shrink depending on how much data you actually have, unlike an array, which can't do that. So those are, I think, probably the biggest sort of trade-offs between arrays and lists. The other thing to keep in mind, though, is that lists being objects do require that different usage of calling the constructor and then calling methods upon that instance, as opposed to arrays, which are in this halfway in between area of sort of like objects, but not really objects, but kind of like. And so it does look a little bit different. Um, the other thing that I think is important to keep in mind about lists and data structures in general, especially as you get to the next class, you're going to start being asked things. You're going to be start thinking about the properties of various data structures. So there are lots of different properties that we care about. But just to give an example of some types of properties that we care about, one thing that we can do with lists is I can have the same value more than once if I want to, right? So I can have duplicates. I can put the value of red in there as many times too. Not all data structures allow me to do that. Some data structures disallow duplicates. That's something we will probably actually talk about a bit later on today. So that's something that we kind of care about when discussing data structures. Another thing that we care about when discussing data structures is whether the values in the data structure are ordered or not. And since lists are so much like arrays, I hope it's clear to see that yes, the data in a list is ordered. If I put the data in a certain order, I can get the data back out in that exact same order if I want to. So it keeps track of that order for me. Again, not all data structures are going to do that. And we might actually see some examples of that a little bit later on today. So just trying to get you a feel for, this world of data structures, how we think about data structures. Any questions on this example before we take a look at another data structure? Yes. Can you do 2D lists? That is a fantastic question. Uh, the answer is not really, but if you really wanted to do a 2D list, here's what you can do. I can do a list within a list. So I know this looks a little bit crazy with all the different brackets, but I can have a list within a list. So I get something out of the list, and that thing is in fact a list. So then I have to get another thing out of it, which means that in order to do that, I have to have two method calls to get. Unlike an array, a 2D array, where you just have the square brackets right next to each other, if your data is truly two-dimensional, I would argue that is another great situation where I probably want to use an array over a list. Two-dimensional arrays just work really nicely if your data fits that format in a way that lists can't quite get you there, at least not as conveniently as arrays can. Great question. Yeah, any other questions before we move on to the next example on our to-do list for today? So lists are an easy one to talk about. Lists are a nice one to start with because they are so similar to arrays. This next data structure that I'm going to talk to you about, though, is not similar to an array, and it's very different from an array. However, it's also extremely useful and extremely common, probably one of the most common data structures that you might come across as you're writing code. And that data structure is actually not a set. I'm going to skip over sets. I know there is a little thing in here about sets. But I'm going to skip over that one. Sets will not be on the exam, actually. I want to make sure that's clear to everybody as well. No sets on the exam, not going to happen. With a tiny little exception that you may see a little bit later on. The next data structure that I want to talk to you about is a map. So with lists and arrays, as we talked about, there's an order, there's an index associated with every value that starts at 0 and counts up 0, 1, 2, 3 till I hit the last thing in my array or the last thing in my list, whatever the case may be. Maps are not like that at all. So what maps try to do is they say, well, that idea of starting at 0 and counting up is useful in some circumstances, but also very restrictive in other circumstances. What if I don't want my index to start at 0? What if I wanted my index to start somewhere else? What if I don't even want my index to be an integer? What if I wanted my index to be a string or something else instead, a double, right? Trying to relax some of those constraints that are imposed on us by using arrays and lists and making things a bit more flexible. So what maps do instead of using an index, is they store every piece of data in what's known as a key value pair. So everything is stored as key value pairs, where the type of the key could be anything. It could be an integer, could be a string, it could be some other type of object entirely. It could be like a student or a fraction, right? One of those kinds of objects as well, if we wanted to. So it's really sort of a create your own index kind of situation, right? Instead of just using the standard 0, 1, 2, 3, etc., I now get to say, hey, I want my index to be this type of thing. And then the values can also be any type of thing as well. The idea is that when I add things to the map, I have to add it in key value pairs. So I have to say specifically, here's the key and here's the value associated with that key. And then later on, when I wish to retrieve stuff from my map, I can say, hey, here's the key. What was the value associated with that key again? And the map will say, here you go, here's the value that I had associated with that particular key. So in order to take a look at how maps work, let's work our way through this phone book example. Right up here at the top, this is calling our constructor. There's a couple clues as to why that is in fact the case. The biggest clue that I think in terms of calling the constructor is that one right there, that new keyword. Really want you to get used to that idea. Anytime you see that new keyword, oh, I'm about to call a constructor, unless it's an array. That is like the one exception, right? Every other time we see that new keyword, we're about to call a constructor. So here you can see, just like before, on the left-hand side, I use map. On the right-hand side, I use hash map. It's the same idea. Just like there's many different kinds of lists, there's also many different kinds of maps. Hash map is a very common one that you'll see used. A tree map is also another very common one that you'll see used. Just like with lists, I don't care if you know the difference. In this class, doesn't matter to me. In a data structures class, they probably do care if you know the difference. But in this class, I don't care if you know the difference. I just care that you know how to use one of them to write a program similar to this. That is what I'm interested in. So you don't need to know the difference between these things, just need to know that they exist and how to use them. So here, actually, hang on, I'm not quite done with this line yet. Notice that when I am saying what types of things are going into this map, there's not just one type, like we saw with the list. So this is clearly a list of strings. But when we're declaring maps, I have to include two types. This is the type of the key, and then this is the type of the value. So I'm using strings for my keys, and I'm using integers for my values. Okay? So this is going to create a brand new map for us. This is going to be an absolutely empty map. There's not going to be a single thing in it. It's going to be 100% empty. But just like we saw with the list, the way that we interact with our map is to call methods on it. So here you can see that I'm calling phonebook.size. That will tell me how many things are in my map. And, I'm trying to actually represent a phone book in this particular example, meaning that if I were to look at a key value pair, I would see someone's name for the key and then a phone number for the value, right? And so the first example that we see that I try to access in this code is right here. I say, hey, go try to get the phone number for Ghostbusters. But wait a second. I just created this map. There is absolutely nothing in it yet. It is empty. I haven't even talked about how to get stuff into the map yet. And I'm already going to it and say, hey, tell me what you have for this. That's interesting, but also important. It's important to know what's going to happen in that situation because here, just to illustrate, is the situation we're dealing with. I'm saying, hey, here's my new map. The size is absolutely 0. What is the phone number for Ghostbusters? It is null. If I ask a map to tell me the value for a key that it doesn't know about, that it has not seen before, it is going to say, oh, that's its way of saying, I don't know. I've never seen this before. I don't know what key you're talking about. So how do we fix that problem? We actually give it some key value pairs to work with. We use the put method. So unlike an array or unlike a list where I am going to place something at a particular index, at a particular position, here I'm going to associate it with a particular key. So the way to interpret this line of code is to think that, okay, hey, I'm going to put a key value pair into this map that says the phone number for Ghostbusters is 555555. So that's what I'm saying by running this statement. I'm saying, hey, there's now an association in my phone book that says the Ghostbusters phone number is all 5s. And if we scroll down and look at what happens after we add this, you can see that, oh, when I look at my map, it actually shows me that key value pair. It tells me that the size is 1. And now when I run this phonebook.get method call, say, hey, tell me what the phone number is for Ghostbusters. It gladly returns all 5s. That's the main way to interact with a map right there. If there's one important thing that I want you to know about using maps, it's this. We put in values with key value pairs, and we get values back out by saying, hey, here's the key, and then it tells me the value. All right. Now let's go on and take a look at what happens next, because there is some other things that are worth knowing about maps. You can see that this example goes on and adds a couple more numbers. So here I'm going to add in 2 more phone numbers and print out the results again. And actually everything works kind of as you would expect. But notice this right here. Notice that when I print out the map, well, wait a second. I added Ghostbusters first, and then I added Jenny second, and then I added Saul Goodman third. But when I print out the map, I get Saul Goodman first, and Ghostbusters second, and Jenny. What does that tell you about maps? Do maps care about order? They do not. They do not. Maps do not track the order that things were put into them. Maps do not will not remember the order that things were added or removed, and they will not be able to tell you that information if you need it. If that is important information to you, if the order of things matters to you, then a map probably isn't the right tool for the job. You should probably look at a list or maybe an array. because those data structures do keep track of the order of our data. So that's one of those important properties that we like to think about. Maps are great for lots of things, but keeping track of the order of things is not one of them. So if order matters to you, map is not the right tool for the job. Let's talk about duplicates. Duplicates is a little bit tricky because we have to think about it both in terms of the keys and in terms of the values. So when it comes to whether maps care about duplicates, the question is, uh, do I see the same key showing up more than one time? And so far the answer is no, but I haven't really tried. Let's talk about values. Do I see the same value showing up more than once? Actually, I do. You can see that, as it so happens, Saul Goodman happens to have the same phone number as the Ghostbusters. So I can have the same value appear more than once. That is allowed. Maps do allow duplicate values. What about keys? Do maps allow duplicate keys? In order to test that out, we can see that, okay, the very last line of the example says, hey, put this value in for Ghostbusters, where you can see that this phone number is different than the original phone number. So what's going to happen? Am I going to see two entries for Ghostbusters? Or am I just going to see one entry for Ghostbusters? Let's take a look. All we really need to do to verify is to print out our map one final time down here at the end. Out our phone book. And we'll run this code one more time and take a look and see that, when I look at the map after I tried to put Ghostbusters in for the second time, you'll notice that Ghostbusters only shows up once. And it doesn't show up with the all fives number. It shows up only with the second number that was added. So keys cannot be duplicated in a map. A key can only show up one time. If I try to put in another value for a key, it just erases the old one and replaces it instead. So when it comes to order, maps don't care about order, lists do. And when it comes to duplicates, lists will have duplicates. And maps will have duplicate values, but not have duplicate keys. So I can't have more than one phone number for Ghostbusters. It's not allowed. It's not a thing that I can have. Are there any questions? Did I see a yes? The setter? I mean, you can kind of think of it as like a setter in a way, in the sense that the key is a field name, for example. But in this case, all of the fields would have the same type. They're all integers, which is maybe not true in a class, right? They can have lots of different types. So I would hesitate to use a map to represent fields within a class. They're not quite the same thing. Also, keep in mind that I could very easily have integers for my keys if I wanted to, or I could have doubles for my keys if I wanted to, or I could have students, right? We had a student class last week. I could have students for my keys if I wanted to, or fractions, or any type that I can think of, any object that I can think of. So the flexibility with maps is immense, which is a good and powerful thing. Yeah. Another question.
Difference between using integers spelled out ints when you're defining a map?
Yes. Yes, there is, and I'm glad that you noticed that. This is, I don't know, maybe a slightly unfortunate detail, I would say, I guess, about the way that Java works. If you try to put the word int here, it won't work. It actually won't work. Remember that these are not objects. They're not classes. Ints are what we call primitive types, right? And so the reason why these don't work here is because anything that has to go inside of these angle brackets must be an object. So I cannot use primitive types here. So what they did to solve this problem is that they made an integer class. And that integer class basically does all the exact same things that an int does. It's just an object as opposed to not an object like int. So you'll often see them used interchangeably in code. In fact, you can often use them interchangeably within code. But if you're using maps or lists or other type of data structures, you have to use the capital I integer class. You cannot use the lowercase I primitive type class. It's a confusing little detail that I personally wish didn't exist, but they didn't ask me when they were making up the language, so we just have to kind of roll with it. Yeah. Good observation though. Any other questions or comments on this example? I think I have one other example to talk to you about today, and it's actually not related to data structures. This is kind of a loose end, I guess, but an important loose end for us to tie up, relating to equality and objects. So when it comes to determining the equality of an object, turns out that it's complicated than you might think. We've learned about using double equals, right? And double equals is great for checking to see if two integers are the same. So if 7 is equal to 7, that makes sense, right? But with objects, it becomes a little bit more complicated. And it turns out that there's two types of equality that we care about. There's not just one type of equality that we care about, but actually two types of equality that we care about. We care about the type of equality where I have two objects that are identical, but actually two separate objects, right? So I call that the identical twin situation, right? Where I have two things that look and are essentially exactly the same for all intents and purposes, but are in fact two distinctly separate objects. But we also care about the case where I'm actually just looking at one object and I want to know if, hey, if this object that I'm looking at is the same as this other object, then am I looking at the same one? I know that might be a little bit abstract, a little bit difficult. So what I want to do is difficult to understand. So what I want to do is go through an example and draw out a diagram, draw some pictures to explain what I mean. So I'm going to look at the person class here. It's a very simple person class. There's a name and an ID field. There's a lot more stuff that we could have included in this class, but for the purposes of this example, this is fine. And then here, I want to point out, this is the first example of equality. This is the first example of equality that I was talking about. This is the dot equals method. So the equals method exists in every single class and every single object, but a lot of times and we saw this last week, right? We'll override it and provide a different version of equals. The big thing to take away here is actually, all of this stuff, the first, basically all but the last line, it's all kind of standard stuff that you don't even necessarily need to think about or worry about too much. This is stuff that I would include in every single equals method that I've ever written, more or less. This line is the one that matters. The way that the way that this equals method is checking for equality is to look at the instance variables, the fields of the two objects. If the instance variables are equal, then it's going to say that the two objects that it's comparing are equal. So it's making that equality determination based on the instance variables contained in the objects. Let's take a look at this example down here, and I'll show you exactly what that means, and draw a little diagram as well, because if you recall from when I was up here a couple weeks ago talking about objects, right, I sketched out some, sort of a mental model of how objects work and how references work. That's going to come in real handy for us now when working through these examples. So I'm going to start with the very first line here. This is, again, calling the constructor. But recall from our conversation a couple weeks ago that if I wanted to illustrate what this looks like, then I would draw a circle on my diagram, like so, and then just write the instance variables inside of here. So name would be John Smith, and ID would be 1. So that takes care of the right-hand side of the equal sign, right? That circle takes care of this. To represent the left-hand side of the equal sign, then I'm going to draw an arrow. Like so. And label it with the variable name. Does anybody remember what that arrow is called again? There's a word for it. It starts with an R. Anybody remember? Rhymes with Preference. Oh, that's too easy. Yes. That was a bad pick. Yeah, it's a reference. It's a reference, not my finest work. But yeah, these are called references, whereas the circle represents the actual instance of the object that was created. So that's the first line of code. And for the second line, I would actually do a similar thing, right? I'm going to go ahead and do that very fast here so that I can move on to the more interesting part. We're going to create our second instance called the constructor. Notice the name is the same, but the ID is different. This is not unusual, right? Very possible for two human beings to have the exact same name, but be different people, right? Have different social security numbers, different student ID numbers. Happens all the time. Happens in this class all the time. I think we have two students with the same name this semester in this class. Happens all the time. So we'll add our reference here for this verb, and that's called P2. Great. Okay. So here we go. I've got two objects, and the very next line is going to call equals. It's asking the question, does P1 equal P2? But it's using dot equals. It is not using double equals. We're going to get to that in just a second. It's using dot equals. So the way to interpret dot equals is, I'm going to follow the reference and I'm going to compare the instance variables. In particular, you'll notice that we ignore the name instance verb because it's very possible, as I said, for two human beings to have the same name but be different human beings. And instead, we just compare the IDs. In this case, even though the names are the same, the IDs are different. So P1 dot equals P2, I would expect to be false. The instance variables don't match. So dot equals is false. And if we run this program and take a look at what gets printed out, we'll see that the very first thing that gets printed out is in fact false. But let's keep going on because this next line of code is perhaps deceptively interesting to us. This is not calling a constructor. How do I know? How do I know it's not calling a constructor? Yeah. No new keywords there. Not calling the constructor, not creating a new instance. This means that I'm not adding any new circles to my diagram. So what am I doing? How would I update my diagram? What am I creating? I am creating a new reference. I'm creating a new arrow. I'm creating an arrow that's called P3. And I'm saying that the arrow called P3 is going to be pointing at the exact same thing that P2 is pointing at. So, okay, the way to update my diagram to reflect this is to draw another arrow like this. And this arrow is going to be labeled P3. Now, wait a second. Why would I ever want to do this? You might be wondering. This seems a little bit of a strange thing to do. Why do I need to have two different things pointing at the same object? I would argue that as human beings, we do this all the time. When I walk around campus and you all see me walking around outside, you say, "Hi, Professor Shook, how you doing?" When I go home, my 7-year-old daughter doesn't call me Professor Shook. That would be really weird, right? That would be extremely strange. She calls me Dad. Sometimes she calls me Doug, and that's really weird. I much prefer when she calls me Dad. Right? Professor Shook is a reference to me. Dad, at least in some parts of the world, also a reference to me. But actually, wait a second, you also have a reference to Dad, right? That is not me, at least not as far as I'm aware, right? Your reference to Dad is pointing somewhere else in the world, right? So, but Professor Shook, your reference for Professor Shook is still pointing right here at me. So that leads us to another type of equality. Do these two references, are they referring to the same thing? If you go to my daughter and you say, "Hey, is Professor Shook Dad?" The answer is yes, right? I am Professor Shook, and I'm also her dad. But for anybody else that's sitting in this room, if I say, "Hey, is Professor Shook dad?" The answer is no, definitely not. Right? Professor Shook is a person, and my dad is a completely different person. So that brings us to a different type of equality. Are two references pointing at the same thing? right? That's the type of equality that we're getting at. And that's the type of equality that's represented by double equals. So when you see double equals used, you actually have an additional kind of level of interpretation that you have to think about. Am I referring to an object? Because if you're referring to an object, you're asking a different question than if you're using double equals with something that's not an object, like an int, right? Or a Boolean. We know how to use double equals with those things. With an object using double equals, I'm asking the question, does the reference on the left-hand side point to the exact same instance as the thing on the right-hand side? So let's take a look at some code examples of that. Here, we're actually not using double equals. We're using dot equals. So P2 dot equals P3. Again, remember, the way that dot equals works is by comparing the instance variables. So if I look at the instance variables for P2, specifically the ID, and I look at the ID for P3, are they equal? Yes, actually, yes, absolutely they are. They happen to be the same exact person. That honestly doesn't matter for dot equals though. All that matters for dot equals is, do the instance variables match? But let's keep moving on to the next one. Here we go. Now we're asking the question, all right, P2 double equals P3 is saying, does P2 point at the same instance as P3? So to answer this question, P2 double equals P3, follow the arrow for P2, follow the arrow for P3. Did you end up at the same circle? If you ended up at the same circle, true. If you ended up at two different circles, false. Question.
So if I have a for each loop with like an array of like students, for example,
Yep.
does that create a whole bunch of new references? So if I'm using double, if I'm checking if the copy is the same as the whatever student like this is equal to the copy of this, they're pointing to the same object.
Yeah, that's a great question. You're asking about a for each loop. So, and I think that's a great question. For a for each loop, I don't actually have a list or anything to use, so I'll have to try my best here with just making stuff up. But I would say for person P in, persons or whatever my name of the list is, this is creating a new reference right here, person P. I'm creating a new reference. Every time I move through the loop, person P is going to be pointing at a different instance, right? So the first time through the loop, P is going to be pointing at the first thing in my list. The next time through the loop, it'll be pointing at the next thing in my list. So really, I'm only creating one additional reference, but that reference is being updated every trip through the loop. Does that answer your question? Yeah. Yeah, it's a great question and a great way of, trying to rationalize how these programs work. It definitely does matter, does make a difference. So, yeah, we can see that P2 double equals P3 is true because they do, in fact, again, I'm looking at line 52 here. P2 double equals P3 is true. They point at the exact same instance, right? So that is going to be 100% absolutely true. But now, wait a second. I'm going to create, this time I am creating another instance, right? So I am creating instance number 3. And you may notice that, this instance looks an awful lot like one of the other instances that we already have, which is not an accident, right? The name is John Smith and the ID is 2. Huh, that's interesting. The other person also has an ID of 2. But here's the reference that gets drawn, and this time this reference is called P4. And so now let's really run this through and take a look at the equality, the different equality questions that we can ask. Here I'm saying P4 dot equals P3. So again, dot equals, I'm paying attention to the instance variable. So I follow the arrow for P3 and I say, the ID is 2. I follow the arrow for P4 and I say, the ID is 2. So dot equals in this case is going to in fact be true. What if I flip-flopped it? What if I said P3 dot equals P4? What would that be? P4 dot equals P3 is true, then P3 dot equals P4 is also true. That's always going to be the case. If I do dot equals in one direction and then I flip it around, it should be the same in the other direction, whether it's true or false. Equality, that's how equality works, right? I can flip the order and it's still in fact the case. Let's talk about double equals though. The first question that we're asking is P3 double equals P4. So again, notice that P3 is pointing to this instance and P4 is pointing to this instance. So because they are pointing at different circles, P3 double equals P4 is false. So in this case, P3 dot equals P4 is true. The instance variables match, but P3 double equals P4 is false. They are two distinctly separate instances, right? When double equals is true with objects, what that means is that both things are, there's only one instance, right? If double equals is true, then the thing on the left and the thing on the right are the same thing. Two different names for the same thing. That's what double equals is testing for. So we can see in this case, I have two identical twins with the same name and the same ID. That's good enough for dot equals. Dot equals is the identical twin checker. It says, yep, these look identical. The instance variables match. But for double equals, that's not good enough. Has to be pointing at the same instance. Another thing I think to keep in mind is if P2 double equals P3 is true, which in fact it is, then P2 dot equals P3 must also be true. Always, 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 always. If I'm comparing two objects and the double equals comparison is true, then I already know that the dot equals comparison must be true. If double equals is true, that means there's only one instance there. And if I'm only looking at one instance, then I would certainly hope that the instance variables would be equal, right? If they don't, then I'm in some weird quantum state or something. I don't know. Some weird warp in space-time continuum where the same object can live in two different simultaneous states, and that's not the world that I'm familiar with. So that would be a different class entirely. But yes, I think it's very important to understand. This comes into play a lot the more you use objects. The more you use objects, the more you use data structures. So an important concept for you to understand. And I guess I'll leave you with this thought for this example. I promise you, absolutely 100% promise you that on the exam 3 that's coming up, I'm going to ask you a question, a code reading question that looks pretty similar to this example, right? And there's already lots of other similar code reading examples in the exam prep repository that we'll practice a couple weeks from now when we get to our exam review. Does anybody have any questions? Anybody have any questions? All right, that's all I have for you. So let's go ahead and prep for the quiz. Go ahead and put your electronics away. I'm going to start the quiz at 1:55 p.m. So please go ahead and put your phones and computers away.